This is Calculus 2 video lecture number 28 on curves defined by parametric equations. We're starting a new unit on parametric equations and polar coordinates. And if you need to go on and take Calculus 3, really make sure that you master the material here because it's going to definitely be used extensively in your future studies of calculus. All right, so let's dive in. So far, we've dealt with curves where y was defined explicitly as a function of x. So we dealt with equations where we could write y equals f of x. Or in some cases, x was defined as a function of y, and usually we would refer to that as x equals g of y or something like that. And then we've also dealt with curves where y was implicitly defined as a function of x. So remember, in those situations, we would write f of xy is equal to 0 or a constant. So in this third case, you're not always able to explicitly solve for y in terms of x, but no problem, right? We've learned how to take derivatives, etc. Now we're going to look at curves where x and y are given in terms of a third variable called a parameter. So we're going to typically deal with two equations, x and y, and each of them are a function of t, where t is the parameter. So they come in a set like this: x is equal to f of t, y is equal to g of t, and we refer to these as parametric equations. And then when you move on to Calculus 3, then your parametric equations will include one more equation, z, as a function of t as well. Now let's get some definitions out of the way. So parametric equations are equations of x equals f of t and y equals g of t, which are given as functions of a third variable t. T you do not see when you graph. Okay, so you're still just going to be tracing curves in the xy plane. You're not seeing what t is doing graphically. Each value of t determines a point xy, so that's what you see, which we can plot in a coordinate plane. And as t varies, the point xy, which we could write as f of t, g of t, that varies, and it traces a curve, which we'll call a parametric curve. Keep in mind, for parametric equations, the direction of motion matters. So we're going to indicate that on all of our graphs. And your parameter is always increasing. So you'll not have to worry, oh, what values shall I plug in for t to determine the direction of motion? T will always be increasing, and as t increases, then it traces out the curve. Okay, you could think of t, we didn't pick it arbitrarily, a lot of the time it does represent time. So in general, the curve with parametric equations, x equals f of t, y equals g of t, and t between a and b has an initial point f of a, g of a, and a terminal point f of b, g of b. If no limits or bounds are given on the parameter t, then you can assume that it takes on any value within the domain of the parametric equations, x and y. All right, so we will start off just nice and easy breezy and just plot some points and get a feel for what's going on. So example 1, sketch the curve by using the parametric equations to plot points. Indicate with an arrow the direction in which the curve is traced as t increases. So notice in this case, they are giving me limits on the parameter. T is only varying between 0 and pi. So I'm only going to plug in values between 0 and 2 pi inclusive for t. And then I'm going to figure out what the x and y values are by using the equations given. So x equals 2 cosine t, y equals t minus cosine t. And then it's up to us exactly how many values we want to plug in. Just enough to get a nice graph. And I'll show you later on, once we can kind of recognize what the graph's going to look like, then you may not need to substitute in so many. So I did quite a few. I did 0, pi over 4, pi over 2, 3 pi over 4, pi. So I just did increments of pi over 4. Then we have 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. And then from here, you can just plug this in your calculator. Make sure you're in radian mode. And I have the following. You can just confirm, okay? So 2, obviously 2 times cosine of pi over 4, that's rad 2 over 2. So if I multiply by 2, then it's just rad 2, which is about 1.4. This is 0, negative 1.4, negative 2. Same thing here, 0, 1.4, and 2. And then to get the y values, now you're going to substitute in the values of t into the equation t minus cosine of t. And just confirm, you should get the following: negative 1, 0.078. I mean, honestly, that's a lot of decimal places. No one's going to notice if you plotted 0.078 or 0.08. So you don't need to go too overboard with the decimals here. 1.57, 3.06, 4.14, 4.63, 4.71, 4.79, and 5.28. Okay, so here's how it works if you've never seen parametric equations before. This right here is our first ordered pair. That's actually going to be the initial point on our graph. So 2, negative 1, that's our initial point. And then here's our next ordered pair, 1.4, 0.08, so on and so forth, 0, 1.57. I don't normally list them out, but I will. It'll just make it easier to graph, and in case you've never seen these before, I think it'll help. 3.06, negative 2, 4.14, negative 1.4, 4.63, 0, 4.71, 1.4, 4.79, and then 2, 5.28, and then this is our terminal point. Because notice that last point came from substituting in 2 pi for t, and that's what the end of the upper limit is on our parameter, the bound, okay? So now let's plot it. It looks like in the x direction, we just live between 2 and negative 2. And then in the y direction, we go down to negative 1, but I have to go up to a little more than 5. Okay. So let's do it. And let me scoot this over. I just had an idea. So not too much negative y, right? We said that. Okay, so here's the x-axis, y-axis. It's going to go up to 6. 1, 2, 3, 4, 5, 6. Love it. Looking good. Does your graph look nice? Take pride. Be a strong grapher. It'll set you apart. Negative 1, and then 1, 2, 3. Let's go the other way. Okay. Looking good. Then I have this bright idea. Let me put this right next to the graph so I don't have to keep scrolling. Shrink it down. Perfect. Okay. So here we go. 2, negative 1. That's my initial point. And sometimes I do like to indicate, hey, guess what? This comes from substituting in t equals 0. Then we have 1.4.08. Okay, so 1.4 and then just barely above the x-axis. Love it. 0, 1.57, that looks like it's there. Negative 1.4, 3.06, maybe around here. Negative 2, 4.14, so 4 and a wee bit more. And then, oh, look at what's going on here, that it's turning back around, negative 1.4, 4.63. Ooh, okay, let's trace out what we have so far. Let's going, it's going, it's going. Changes its mind. And we can put these little arrows here to indicate the direction of motion. Let's see, I stopped here, negative 1.4, 4.63. Then we've got 0, 4.71. Okay, 1.4, 4.79. So it's just barely coming up here. And then 2, 5.28. So maybe here. And that's the terminal point. This comes from t equals 2 pi. All right, make sure when you're given limits on your parameter that you clearly show the initial and terminal points. If there's no limits on the parameter, then make sure you indicate that you have arrows when appropriate. All right, so that's that first example. How was it? Very good. Let's move on and look at something else. All right, example 2 says sketch the curve by using the parametric equations to plot points. Indicate with an arrow the direction in which the curve is traced as t increases. And then part B, eliminate the parameter to find a Cartesian equation of the curve. So if you'll notice here with these parametric equations, there's no limits given on the parameter t. And I noticed that for both equations, x and y, I can substitute in any value of t and they will both be well defined. So it's up to you, kind of use your judgment, what you want to start off with. I'm going to go from like -3 to +3 for my parameter t, see what sort of values I get for x and y, and then I'll determine from there if I feel like I need to plot more. Okay, so here's t, x, y. And I said we'll start from -3, go to +3. That should give us like a nice starting off point. So -3, -2, -1, 0, 1, 2, and 3. And then we'll figure out what the x and y values are that correspond. So let's see, if t is -3, remember I'm substituting that into the equation right here, x equals 1 plus 3t. So I'd have 1 plus 3 times -3, so that's going to be -8. If t is -2, x is going to be, let's see, 1 plus 3 times -2, so that'll be -5. And then I notice that equation's linear, right? So all of these values just go up by 3. So I can just keep adding 3, call it a day. Beautiful. And then for y, it's 2 minus t squared, so 2 minus... Now -3 squared, that's going to be +9. So this is -7. Then 2 minus 4, that's going to be -2. 2 minus 1. 2 minus 0. And then they repeat, right? So 2 minus 1. Then I get -2 again and -7. All right. So let's see here. It looks like x values need to range between -8 and 10. Okay, that's not bad. And then y values only go up to +2, mostly in the negative. So I'll draw my axes accordingly. All right, always look at what sort of points you're going to have to plot before you draw out your x and y axes, so you can do it in a way where you set up for a nice graph. So here's the x-axis, here's the y-axis. I have to go up to 2. So 1, 2. And down to -7. So 1, 2, 3, 4, 5, 6, 7. And then the x-axis has to go -8 to +10. Let's just scale this guy by 2. So that's -2, 4, 6, 8, and then +2, 4, 6, 8, 10. All right. You don't have to scale your axes the same, right? Just label and all is good. Here we go. I'm not going to list the points out. Hopefully at this phase in your math career, you know this is -8, -7. Let's plot it, people. So -8, -7 right here. Then we've got -5, -2. So that'll be about here. Remember, I'm scaling my axes differently. -2, +1. Then I have 1, 2. All right. Then 4, 1, got it. 7, negative 2. So 2, 4, 6, 7, and negative 2 would be here. And then we've got 10 and negative 7. All right, so in this case, I'm still going to indicate the direction of motion. All right. It went down this way. I know it keeps going, so put an arrow on that end of the graph. And same thing here, it keeps going down that way. That's not for the direction of motion. That's to indicate that the graph keeps going. This little arrow here is for the direction of motion. Okay, so as t increases, we went up one side of the graph, back down the other side. Very lovely. That's part A, all done. Okay, check. Part B says eliminate the parameter to find a Cartesian equation of the curve. So let me rewrite the equations here, and I'll show you exactly how we do that. So we have x equals 1 plus 3t, and y equals 2 minus t squared. There's a few little techniques that you can use to eliminate the parameter. One of the most useful is just substitution. So solve for the parameter in one of the equations and then substitute it into the other equation. Since it's going to be easier to solve for t in the first equation, right, since t isn't squared, I'll go ahead and do that and then substitute it into the second equation. So solving for t, I have x minus 1 over 3 is equal to t, and then now let's substitute that in below. So then we have y equals 2 minus, instead of t, I'm going to put x minus 1 over 3 squared. And then let's simplify this a little bit. I mean, I can already tell this is going to be the equation of a parabola. How do I know? Because I have y solved in terms of x, and x is squared. And we just reviewed parabolas. If you want to rewrite this in vertex form, you can go ahead. Notice this is going to give me a coefficient of 1/9. And I still have that negative there, so that would be negative 1/9 times x minus 1 squared plus 2. Okay, and if you'll remember, when we have the vertex form of a parabola, it's written as y equals a times x minus h squared plus k, where the vertex is at h comma k. And so here I can tell, okay, the vertex of this parabola is at 1, 2. And indeed, that's what we found when we graphed, right? Oh, look, there's our vertex. Beautiful. Okay, so as you can see, it's very useful sometimes to eliminate the parameter so you can identify what sort of curve you're dealing with, and that can make it more straightforward when it comes to graphing. So you're not just plotting points without a clue as to how things are going to turn out, but when you already know what sort of curve to expect, life can be easier. So let's practice doing that some more. So example 3, eliminate the parameter to find a Cartesian equation of the curve and sketch the curve. Now this little scenario comes up so much, so I wanted to show you the technique. We have x equals 4 cosine theta and y equals 3 sine theta. Now, anytime you're working with trigonometric functions, a lot of the times one equation will be given in terms of cosine, the other one sine, or you might see like a tangent and secant. And the reason is because you're going to use a Pythagorean identity to eliminate the parameter. Watch. So we're going to use sine squared theta plus cosine squared theta equals 1 to eliminate the parameter. You will wow your friends when you do this. So we know they told us x equals 4 cosine theta. That means x divided by 4 is equal to cosine theta, correct? So then I can say, all right, x over 4 squared is equal to cosine squared theta. Similarly, since y is equal to 3 sine theta, that means y over 3 equals sine theta, which means y over 3 squared equals sine squared theta. And then if I go ahead and add these together, now I'm adding cosine squared theta and sine squared theta, and what do I end up with? X over 4 squared plus y over 3 squared equals 1. So there, I've eliminated the parameter. Beautiful. Now, part B asks us to sketch the curve. Okay, no problem. Do you recognize this equation? Hopefully you do, because you've just reviewed your conic sections, or you will shortly, but you should have seen them in pre-calc at least a little bit. So this is the equation of an ellipse centered at the origin, right? So just centered at 0, 0. And notice they gave me a restriction on the parameter. In this case, the parameter was theta, not t, no big deal. And theta is restricted between negative pi over 2 and pi over 2. Well, what does that mean? Okay, well, since theta is restricted between negative pi over 2 and pi over 2, I'm only going to trace out part of the ellipse. Can you figure out which part? Well, plug in each of the values. So let's see here. When theta is equal to negative pi over 2, that means x, which is equal to 4 cosine theta, would be 0. And y, which is equal to 3 sine theta, would be negative 3. Okay, so let's see what's going on. We're starting at 0, negative 3, when theta is negative pi over 2. So x-axis, y-axis, I'll go up to 3 and down to negative 3 in the y direction, and 4 and negative 4 in the x direction. Okay, and we're starting right here at 0, negative 3, when theta is negative pi over 2. Now, what about when theta is 0? So when theta is 0, x is going to be 4 cosine of 0, which is 4. And y is going to be 3 times sine of 0, which is 0. So we'll be right here. So here's this portion. And then when theta equals positive pi over 2, then I'm sure you can figure out x is going to be 0 and y is going to be 3. Bada bing, bada boom. So what gets traced out? Only the right half of the ellipse, and it gets traced out counterclockwise. So if you'll notice here, that corresponds perfectly to the limits on theta being between negative pi over 2 and pi over 2, right? Negative pi over 2 is here up until positive pi over 2. And if x is equal to cosine theta and y is equal to sine theta, and your parameter is increasing, your curve gets traced out counterclockwise. So keep that in mind, because later in Calc 3, you're going to have to parametrize curves. Very nice. Okay, we're just going to practice more eliminating the parameter, but not necessarily graphing. Okay, so here we have x equals natural log of t and y equals radical t. They also told us PS, t is greater than or equal to 1. All right, that's probably to make sure everything was going to be nice and well defined. And I'm just going to go for substitution. Now let's see here. Which of the two equations would it be easier to solve for t in? Well, if I use x equals natural log of t, I'm going to have t equals e to the x. I don't know how nice that's going to be. Let me just go to equation 2 right here, because I could just say t is equal to y squared. Okay, and then from there, if I replace that into the first equation, then I get x equals natural log of y squared, which you could leave alone like that, or I would be allowed to move the exponent to the front. I could write x equals 2 natural log of y, because they did tell me that t is greater than or equal to 1. So then that means for sure, since t is equal to y squared, or y equals rad t, t is not going to be negative, y is not going to be negative. And so then we're fine to go ahead and use that property. Either one's acceptable. Now, what if I had done it the other way that I kind of talked myself out of? Would it have been so bad? Let's see. If I rewrote it using the first equation that e to the x is equal to t, if I substitute that into the second equation, then I get y equals the square root of e to the x. So e to the x raised to the 1/2, right? Same thing. And then I end up with y equals e to the x over 2. Well, they don't look the same because this gives me a function of x and the first way gave us a function of y. Which one do you want? It just depends. What are you going to use these equations for? Okay, so it's good to know both ways. I think they were actually both equally tricky, so whatever. Next example, x equals 2 sine t, y equals 4 plus cosine t, and t is bounded between 0 and 3 pi over 2. So we're going to use the same technique that I showed you before in the previous example, where we're going to use the Pythagorean identity. In this case, we just have to do a little bit different style of rearranging. So since x equals 2 sine t, that means x divided by 2 is sine t, which means x divided by 2 squared is sine squared t. And also, since y equals 4 plus cosine t, then y minus 4 equals cosine t. So y minus 4 squared equals cosine squared t. And then we add these together, and lo and behold, we have x over 2 squared plus y minus 4 squared is equal to 1. All right, so this time we have another ellipse. Where's the center though? Good, it's at 0, 4. And I'll let you play around with it and figure out which portion of the ellipse is traced out and in what direction. So notice the limits for t are between 0 and 3 pi over 2. But in this case, x is equal to 2 sine t and y is equal to 4 plus cosine t. So play around with it, plug in, I would say plug in 0 for t, see where you are, plug in maybe pi over 2, then pi, and 3 pi over 2. See which portion of the ellipse is traced out and the direction. You can't just do the starting point and the stopping point. Okay? Comment down below what you get. And last example, couldn't finish this off without some good old hyperbolics, right? So eliminate the parameter, then sketch the curve. So we have x equals 2 cos t and y equals 5 sinh t. We have to use one of the identities that holds for hyperbolics. Do you remember them? So we have cos squared t minus sinh squared t equals 1. Ooh, oh my. Okay, so we're going to start off very similar. I'm going to kind of run through the beginning steps a little more quickly. So we'll have x divided by 2 squared, that equals cos squared t. And then I have y divided by 5 squared, that equals sinh squared t. And remember, for the hyperbolics, this identity involves subtraction. And so now we're left with the equation x divided by 2 squared minus y divided by 5 squared equals 1. Do you recognize this? Oh my goodness. Maybe if I rewrote it as x squared over 2 squared minus y squared over 5 squared equals 1. That probably didn't do anything for you. This is a hyperbola. Okay, the center is at 0, 0. And we're not going to find the foci or anything like that, but I'll just draw quickly the asymptotes. I know it's opening along the x-axis, right? Because x squared is positive here. And either, depending on who your instructor is, you're going to study conics shortly after, or you've just reviewed them. I'll link a video here if you need a review on hyperbolas, okay? So So the center's at 0, 0. I'm going to make the fundamental rectangle. Here's 2, 1, 2, 3, 4, 5, 1, 2, and 1, 2, 3, 4, 5. So I'm not going through the process. This is the fundamental rectangle. You should have seen this in pre-calc, but if not, you are going to review it or you just reviewed it. Depends on what order your teacher likes to do this stuff in. Here's the asymptotes for the hyperbola, and it's opening along the x-axis. Okay, so here's one of the vertices, here's the other one, and it opens this way. Ooh, so snazzy. Okay. So there's our our hyperbolic graph. Do you love it? Good. So this was just an introduction to parametric equations. In the next video, we're going to go over calculus with parametric equations. Stay tuned. Don't forget to give a thumbs up, subscribe if you haven't already. And if you worked out that example that we did right before with the direction of motion in the graph, comment down below what you got so we can get a little discussion going on this guy. All right, stay tuned. Thanks for all your support.